Hi, in this video I'll be demonstrating the solution for the I/O port programming using MPLAB Hardware Development Environment Lab. So I'll be first demonstrating exercise 1. Exercise 1 just asks you to start with the example code that was given here and also on Aula. And just change the values that you're showing. So instead of 55 and AA, you just display whatever you like. So there's many different ways to do this. Here's my project. You'll find this file in the solutions folders. Basically, this is what I have. The biggest difference between my code and the code in the previous example was that I'm not using any variables anymore, and I've chosen a specific values that will give me a nice pattern on the display. So what will happen is first we'll load 0f, and then these values will only illuminate a single LED, and then this will be followed by a mirror image of the first value. But everything else is the same, really. All you have to do is make sure there's enough delays between the values when they're displayed. Let's just run simulation. And this is what it looks like. So the values are such that only a single LED will light up, and then this pattern, and then it will repeat. Let's go into debugging to see this closely. If Proteus will let me. It looks like it won't let me. All right, so we have our output, we have the code here. I'll also add the line numbers so it's easier. And also in here, because we don't have any variables, this output window here is kind of useless. So what we can do is change it. So let's add the CPU registers. And also the watch window. So the watch window is, I find, the most useful out of all of the options that are available here. And just split the output screen with all three of them. Okay, so to add something, right click and add items. Typically it's best to add registers that you are interested in seeing or you're manipulating. In this exercise, you only have 2 registers that we're manipulating, so we're just gonna add them. But in more complicated projects, this is much easier, much useful than now, because we're just loading some values. But if it was something more complicated like ADCs or interrupts, having the watch window really helps to track down what's actually happening. So what I'll do is I'll just put breakpoints on all the lines where I'm loading a value. And you see that I cannot even put a breakpoint on a delay line, which is a good thing. Because otherwise, if I had a breakpoint on a delay line, I would have to single step. I'll have to press buttons for every instruction in a delay, which would take a long time to get through. So if I have a breakpoint just after the delay, I can run the simulation and then it will execute the delay much faster. So I won't have to step through it slowly. Okay, so we're currently on this line indicated by this red arrow, which means that the execution of the program has started, but it has not executed this line yet. So this arrow points to the instruction that is is to be executed next. So if I press step into to execute it. So if you have a look here, we have not manipulated TRISD yet, but its value is FF, and that's the case for all of the TRIS registers. If you can see on the CPU registers, all of the port registers for TRIS, the tri-state configuration, are ones by default. So that means that if you want to change, if you want to use the ports, you must configure them. If you want to use them as something else than inputs, you have to configure them as outputs. And this is done just so that if you have any ports that are not used, or pins that you're not using, and you don't change these values, this will ensure that current leakage through the pins is reduced. Okay, so next line. LATD is 0 by default. So with these lines, we're just ensuring that it is 0. Because in simulation, yeah, it's 0, but if you had the practical device with you, that's not guaranteed. It might be something else, depending on what you have connected to the pins. So there might be some intermittent states that are not detected. And because it's simulation and it's ideal environment, this is a 0, but you cannot be sure of that if you're dealing with the actual hardware. Okay, step in. Now we're about to change the TRISD. So notice that any change within the registers will be indicated with red. So there you go. Now we've overwritten TRISD with 0, 0, making it all outputs. And now we enter the infinite loop where we just loop through the settings, through the values that we have configured for LATD. So first is F0, sorry, 0F. So the first least significant bits are 4. The 4 more significant bits are zeros. Then we go to 1, 2, 4, 8, then 2, that's 1, 0, 2, 0, 4, 0, 8, 0, and then 0F. F0, sorry. Yep, and that's all it does really. It's really simple. Nothing too complicated. And what you can do from here is you could disable disable the breakpoint, so they'll be like hollowed out. And then when you run a simulation, you'll be able to see the changes in LATD and also look at the output, which is pretty handy. And that's it pretty much. So if you have any questions about this, let me know via chat in Teams. And yeah, talk to you soon next week.